Alright, what's up? So this is a simple demonstration of how a wave works, and essentially what we've got is something that turns here and it lifts the string and the wave is passed down. It goes through an open window and then away. We don't worry about what happens to it. So if I hit pulse, what we can see is it lifts and it transfers the energy down that way. This is a transverse wave in this case, because although the wave is moving to the right, the actual vibration is to upwards and then downwards. If I do more than one pulse, then we can start to see that familiar pattern of a wave, and I can represent that even better by setting this to oscilloscope and letting it move up and down by itself. You can see that this wave is getting slightly smaller over time. That's this process called damping. If I get rid of that completely, then it'll stay okay, and that just means that no energy is being lost. So in general, we're going to use no damping when we do these kind of questions. You don't worry about damping until year 13. But for the simulation, actually, I do need to put damping on, otherwise it can cause some problems. Don't worry about that too much though. So let's go with a pulse again then, and just let that drop back to its natural position. What I'm going to change are a few of the features of the wave. So there's my normal pulse. Now you can see the wave speed is pretty steady, it's not changing. The first thing I'm going to change is the pulse width. So if you take a look at that one there, if I make the pulse width much smaller, you can see that it's a sort of smaller wave. The wavelength has gone down. That means essentially the frequency has gone up. I could be creating more and more waves per second because they're smaller. On the other hand, if I make the pulse width much bigger, that's like a longer wavelength, and so the frequency would have gone down. Let's move the pulse width back to about the original position. We've also got the amplitude. If I turn the amplitude right up, then we get a very big movement, and if I turn the amplitude right down, we get just a small movement. Remember, for sound waves, amplitude is the loudness of the sound, and this wavelength, or the frequency, is to do with the actual pitch that you hear. The last thing we can change that we don't normally mess with too much for this is the tension in the string, and that really represents the type of material. So if we turn it down, watch what happens. The wave gets a lot slower, and you can see the individual particles moving up and dragging each other up and falling back down. We said the material is the only thing that affects the wave speed. That's the medium that the wave is traveling through. The amplitude and the wavelength don't change that at all. If we just move back to the oscillating one, we can look at the frequency in a little bit more detail. If we turn the frequency right down, you can see we naturally get a longer wavelength. The wave speed has not changed at all, but the wavelength has got much bigger for a smaller frequency. On the other hand, if we increase the frequency, we can see the wavelengths get really small, really tiny. Hopefully you can just about see the patterns of the wave there. So that's pretty much it that you need to know for the properties of waves. You need to know the amplitude is the maximum displacement from the horizontal position. You need to know the frequency is the number of waves per second. The time period is the time taken for one wave. The wavelength is the length of one wave. And then the wave speed is, of course, the speed of a wave represented by the tension in the string. And we can get some really messy animations going on here if we turn the tension down in this rope.